Yeah, we start.
So, Tangle of the Georgia Institute of Technology will continue telling us about the Habiro ring and other wonderful things.
Thank you. So let me first recall the Habiro ring. So we have here, so it's the Habiro ring. So this ZQ hat, which is the completion, so the inverse limit Q, and we divide by this Q sub n, where this Q sub n here is the standard 1 minus Q squared up to 1 minus Q to the n. So every element F in this Habiro ring can be presented as an infinite series. So F can be rewritten the sum of F and Q, and then Q sub n, and from 0 to infinity, where F and Q here is a integer, it's a polynomial with integer coefficients. Well, actually, you can put here plus minus 1, or you can take here just Q. Because you already saw the last time that actually Q inverse is only in there. So if you add Q inverse, you don't change the ring actually. Okay, and the main property is that you can evaluate this function f at any root of unity. So if Z here is the set of root of unity, so this is just, let me recall that I will consider this as the torsion subgroup of the group, the multiplicative group of non-zero complex numbers. So that then every f in here will determine a function from this Z to the complex number θ. Do you have questions?
Just I didn't see one.
So we can evaluate this function at a root of unity. And then we have a Taylor expansion. Say at 1, then we have T sub 1 from the Habiro ring, to the ring of formal power series in 1 minus Q, or Q minus 1. And one of the main things about this ring, a nice thing about this is that this map here is an injection. Okay, so in particular, this ring here, Z cubed, is an integral domain. Okay, and then we have another thing about the other property of analytic functions. I mean, if F and G are in this ring, and F is equal to G on some set subset Z prime of Z, having a limit point, then F is equal to G. So we have all the properties of analytic functions here.
Just a real quick question. Superficially, this ring looks a lot like the iadic completion of the rings. Is there anything there?
I will connect this to p-adic ring in a minute.
Not
okay?
p-adic, the iadic, the augmentation idea.
Okay. Yeah.
Okay, I see that.
Iadic is Q minus 1 to the end.
Right, so
Yes.
this is just taking powers of Q minus 1. So,
No, this is something
okay,
more.
that's fine. I was curious.
Okay, so so I know that so Mani and Marconi, they well, so Alan Kohn talked about this field with one element, and people are searching for, well, instead of field with one element, they are searching for the ring of regular functions on such field. And Mani and Marconi suggest that this is it. This is the ring of regular function. Ring of regular function on F1. Well, whatever it is, this non-existence. Okay, but now let me, before going to invariant of three manifolds, give a connection between this ring and the p-adic ring. So the p-adic ring, let me recall that. So here, suppose p here is any prime, a prime number. We define so z sub p, the ring of the p-adic integer. So just again, you can define it as the inverse limit of z over p to the n, right? So informally, it is just a set of all infinite a n p to the n, and from 0 to infinity. And here a n is just integers. Well, you can restrict a n between 0 and p minus 1, but in general, any infinite series like that is an element of the p-adic ring. Okay. And now suppose f is an element in the Habiro ring. F and q, and here q sub n. We see that we can evaluate f at a root of unity, but you can also evaluate f at any integer. Okay. So, for example, what is f of 2? F of 2, and you get here the sum, and from 0 to infinity, fn of 2, and then let me write out this explicitly 1 minus 2, and then 1 minus 2 squared, up to 1 minus 2 to the n. Okay. Now, if p is an odd prime, p is an odd prime, then according to little okay, so this little, can you see this? Fermat theorem, okay? P divides 2 to the p minus 1, minus 1, right? So it means that this one here is divisible by big power of p. Because if n is big enough, n is a big multiple of this here, and then there are a lot of terms here divisible by p. So this is divisible by big power of p, and so this sum here is conversion, give us an element in Zp. Okay, so this will be in Zp. The p-adic ring here. Okay, so actually you can see that f2 has a meaning, well, it's just an element of Zp for every odd integer p. Okay, actually this is just an easy exercise. You can show that if you take the Habiro ring, sorry, this is Q, and you put Q equal to 2, which means that you evaluate 2. Then this is actually equal to the product over on odd prime p of the Zp. Okay. This is pretty simple because you just decompose this. I mean, Z is the PID, so when you divide this by product of many primes, you use the Chinese remainder theorem, and then you get a lot of Z over pk to some number nk. And
why is it an equality? I see that it's only an injection.
well, so this one here is product of many primes. Okay, so this is just product of pk to some nk up to some number. Okay, and now it's an exercise to show that if you have this here, you take the limit, the inverse limit. I mean this. So z, and you divide by this pk to nk here, the product here. This is equal to just sum over k of z, and you divide by pk to the nk, right? Mm-hmm. And then if you take the inverse limit, this will give you exactly this product. Okay, so you see that the Habiro ring, when you have this, you can also go into p-adic numbers here. Okay, you can evaluate at any integers, well actually you can evaluate at any rational numbers and even complex number, but then you need to go into p-adic analysis.
I'm sorry. If you take an arbitrary element on the right from the product of ZP,
Yes.
no, lower.
This one?
No,
This one?
here, yes. You take any element of this product, okay?
Yeah.
Then you must show that there is an element of the Habiro ring F such that its evaluation at 2 is equal to the right-hand side.
Right,
Yes?
yeah.
Is that true?
Yeah, that's true.
Okay, well, I just don't see proof.
Yeah, I mean, you just take, yeah, but, if you want, we can discuss that later.
Okay, I'll think about it at home.
Okay, so let me return to invariant of north and base. So let me recall, well actually I will recall the definition a bit later. So the general Reshetikhin-Turaev invariant of three manifolds is that if G is a simple Lie algebra, M is an oriented closed three manifold, and a root of unity psi, which the order of which must, well, there are some restrictions, so I will write here just these of G. Well, for example, we can define this as require the order, so something like the order of psi must be bigger than or equal to the dual of the number of the Lie algebra, and then the order of psi is a multiple of, well, the ratio between the long root and the short root. So you take here the length of the long root, you divide by the length of the short. Well, you take the square. And this number is either 1, 2, or 3 for every simple Lie algebra. So usually there are some lesser restriction here, but for example, if the order of psi satisfies these two.
So what is Z and G?
G is the Lie algebra.
No, what is ZG?
Z sub G. Okay, so this is the set of rootability so that the order of psi satisfies these two conditions here. Okay, and for this one we can define the WRT invariant. So I will denote by just tau. This is the WRT invariant tau m G of psi, which is the complex number. And I will recall the definition of this WRT invariant a bit later. Okay, and now the main theorem is the following. So this is the in joint book with Habiro. To start, suppose M is an integral homology tree-sphere. So this means that the integral homology of M would be the same as that of the tree-sphere. So this is H M. Z is the same as the homology of S3. Okay. Then there exists a unique invariant of M, so I will call that Jm. So there's some G here, because it also depends on the Lie algebra in the Habiro ring, such that whenever the WRT invariant can be defined, so that for every this sign in this Z sub G, the value of the WRT invariant is the same as the value of this invariant at that point. So but we have here tau and G of psi, which is defined now because psi is in here, is equal to this Jm at psi, which this one can be defined at every root of unity. Okay. So in a sense, you can extend the definition of the WRT invariant to every root of unity. Okay, so I should say that when G is equal to SM2, it was the result of Habiro, and this when he defined the Habiro ring. But this proof use some explicit properties of SM2C and cannot be generalized to all of the Lie algebra. So we work out a new proof, which is more conceptual than the one of SM2 here. And then another theorem is the following, which say that for every knot K, so for every knot K in S3, there exists an invariant, again a unique invariant, so I sub K, which is in the Habiro ring, such that, again, for every sign in Z, the set of root of unity, the value of this invariant at psi here is equal to the Kashayev invariant at psi. Well, Kashayev invariant is defined at the first root of unity, so I will write here for zeta, well, maybe. So I write here zeta sub n. This is also zeta sub n, where we call that zeta sub n is the just exponent of 2 pi I over n. Well, actually, when I prove this, this is for every Lie algebra G, but then for that case, I have to define what is Kashayev invariant. For SL2C, this is the ordinary Kashayev invariant. So this is for SL2. This is the usual Kashayev invariant. Well, I should say that in the SM2C case, this is much easier. I mean, this for instance is actually an easy result. But I just would like to show that there are many invariants in quantum topology take value in the Habiro ring. Okay, and one is there. You see that it's a really nice function. You can have a well, it has strong integrality there. Okay, so for example, you can ask about topological interpretation of the coefficients or things like that. So maybe there's some intersection or dimension and things like that. Or if you want to categorify the WRT invariant, you certainly need some integrality. Okay, so I will now explain, well, recall the definition of this WRT invariant. Then I will tell about consequences of this main theorem, and then if I still have time, I will tell you about the construction of this. So we call this unified invariant here, because it's unified on the WRT invariant into a function.
None of those theorems have anything to do with p-adics. Why did you introduce the p-adics?
Well, it's just just some properties of the ring. Yeah. So once you have things there, you can define invariant. Evaluate. So originally you have just function from set unity to complex numbers, but now you can also define invariant with value in the p-adic ring, because you can lift to this set of functions. Okay, so let me now recall the definition of the WRT invariant. So we begin with invariants of knot and links. And so the Kirby calculus will tell us that, so if you have a link, which is a framed link in S3, then you can construct a three-manifold M, which is you do surgery along the link. Okay. And then Kirby theorem will tell us that this map here, so you map links here, you map frame links, to three manifolds by this one here. It will be an isomorphism as a set, just one by one dijection if you divide this by the so-called Kirby move, K1 and K2, where the Kirby move, well, K1 here is the stabilization. It means that if you have a link, you can add to this a driven link with plus or minus one frame. So just, and then the other move is the handle slide. If you have this one component, this another component of the link, you can move this to this one here. You can slide this one, the first one to the second one, and you get a new link. So this is K2. Okay, so Kirby calculus tells us that if you do surgery on two links and you get the same three manifolds, then the two links are related by a sequence of these two moves. And conversely, I mean the converse is easy. Okay, so in order to construct invariant of three manifolds, if you have an invariant of frame links that is invariant under these two moves here, then you have an invariant of three manifolds. Okay, so now the theory of quantum invariance is that you begin with a D algebra, and L is the K component link. And D1
in the sphere.
Sorry?
A link in the sphere, or
yeah, this is link in S3. This is link in S3. Link in S3 here. Okay. So then you can produce the invariant JL of V1 up to Vk here, which is a Laurent polynomial in some fractional power of this quantum variable here. Okay, so we call these the colors here. We call the colors of the link. Okay. Well, the color here, it is just a G model. Okay, so by linearity, we can extend the colors to an element. So the color can be considered as you can take any element of the ring of representation, the ring of G models. And you still, so it means that instead of D1 here, you take any element because it's just linear combination of G models. So we use linearity to extend the invariant when the colors are elements of the rings of G model. So we want a special color, so some omega, the color, such that JL of omega, omega, and so on is invariant under the two Kirby moves. Okay, then in that case you will have an invariant of three manifolds. If you can find such a color, okay, let's call this a Kirby color. It's a Kirby curve. So
there's a little Q missing there at the end of the omegas, right?
Right, yeah. So usually I drop the Q if it's not very important.
Okay.
Yeah. Okay, I can add the Q here. So it turns out that well, just look at an example. In the case G is SL2, so we know that, and V here is the two-dimensional fundamental representation. For every n, you have this V sub n, which is the symmetric power, n minus 1 symmetric power of V. Then this is the unique SL2 irreducible SL2 model, which is irreducible or simple. Okay, so so now which one would be a Kirby color? Okay. Then it turns out that, so this is a, let me call this a, well, maybe let me give an example, because I think it's the, so this is, so if I have here this right hand graph one here, then JK is equal to n. So n here, which stands for the dn here, the n-dimensional representation, is equal to, maybe I divide by n factorial, by n quantum here, is equal to, so q 1 minus n, then you have the sum, k from 0 to infinity, q minus kn, 1 minus n here, 1 minus n, 2 minus n, up to 1 minus q to the k minus n. Well, again, I mean, this is an infinite sum, but I can replace this by just n minus 1, because beginning from the term where k is bigger than or equal to n, you have a 0 term here. Okay, so this will be a terminating series whenever k, so it means that if n is bigger than 0, then this is just actually a finite sum. It's the finite sum. Okay, and we have, and that is the value of this, the color-Jones polynomial of this graph one, we color this by n. Now, if n is less than 0, less than or equal to 0, this will be an infinite sum. This will be an infinite sum. Okay, because every term will be non-zero, it will be an infinite sum. But it is an element of the Habiro ring. Okay, because this property is divisible by, this is divisible by q sub k, It's divisible by this one here. So this one will be q sub k times zq, or maybe plus minus 1. Okay, but actually, the nice thing is that actually, the right-hand side at n is always equal to the same at minus n. So, but identity will be in the Habiro ring. Okay. So, which means that if n is strictly less than 0, although this is an infinite sum, but actually it's a finite sum because it's equal to the one with positive n. So it's not truly infinite there. Okay? The only exception, so it means that the right-hand side is equal to a finite sum. So just a finite Laurent polynomial, just a Laurent polynomial, because it's equal to the right-hand, the one with positive n, so it's just a Laurent polynomial. So it's just a Laurent polynomial. Well, in a sense, we first defined n bigger than 0, that is the, and where n is bigger than 0, that is a real, well, some representation, okay? And then we analytically continue this function from n to minus n, or actually to any integer. And then you will get exactly this one here. And then when n is less than 0, although it's infinite, it's still actually not truly infinite. The one that is truly infinite is the case when n is equal to 0. When n is equal to 0, then this is truly infinite. Okay. You get something in the Habiro ring now, when n is going to 0, and this value n is going to 0 is exactly the Kashev invariant of this knot. This is exactly the Kashev invariant. So Kashev invariant is exactly the color where the value of this, well, this is actually the value of the, well, if you take and you break knot into the long knot or the 1-1 tangle, then you get, this is the value of this when you define by normalize so that this anotic value 1. And in that case, I mean, for most of the color, it will be finite, except for some of them. And one of them is the Kashev, I mean, the color 0 here, and you get the Kashev invariant. Okay, so that's just about the Kashev invariant. So let me return to the three-dimensional invariant. Okay, so let me inform you here. This is the pseudo theorem. Well, because it's not quite a theorem, we should say that if you take the following, so we find f sub l of psi. So psi here is the root of unity of order r. So I will take the sum over all possible color. So I have jk of n1, comma up to nk, and I multiply by the corresponding value of the n naught. Okay, so this all should be easy. Then this is invariant under the Handelsline move, so this K2. So I call this pseudo theorem because actually this expression doesn't make sense in any reasonable way. I mean, this is an infinite sum. But the nice thing with this pseudo theorem is that it has a pseudo proof, which is very simple. Okay? But probably I don't have time to explain this here. It's really simple if you use some formal properties of quantum invariant planes. But it's at least explain why we should choose this. Okay? So to make things work, we need to regularize this sum. So we need to regularize this sum. So you need to regularize the right-hand side. Okay? And there is a nice property of, so far I have not touched root of unity here. So I don't need this here. I mean, for this pseudo theorem. Okay? So I just take, this is just Q, just any Q here. Then this is still Q. Then this is invariant under the Handelsline proof. Okay, so I said there's a simple, very simple pseudo proof of this. And if we can make sense of this right-hand side, then we can define an invariant three-dimensional function. Now let me just, so suppose L is just a knot K. So K is a knot. And now Q is equal to psi, which is a root of unity of order Z. Of order R. Then there's a nice periodicity which say that Jk of n plus 2R will be equal to just Jk of n. But I put here the equality. This means that we have to evaluate both sides when Q is equal to psi. Okay? So if Q is the root of unity, then we have the periodicity here. Whenever you move by 2R, it's still the same. And so one simple way to regularize this sum is that instead of taking the sum from minus infinity to infinity, because you have periodicity, this is just the sum, you should take the sum from 0 to, or any, from 0 to 2R minus 1. Okay? So actually, so this is now reversed now. If I take F L of psi to be exactly the same. So this is the sum. But now n1 up to nk here should be say from 1 to 2r, 2r. I can replace this by 4r, by 6r, any multiple of 2r, because this is just a it's just a fundamental domain of this shift here. And just this one again, so jk of n1 up to nk, and then n1 nk here, and q is equal to psi. Okay. Then this would be invariant under the Handel-Schlein rule. Okay. Now everything can be made precise, and this was more or less the result of Reshetikhin-Turaev, where they proved this in another way. But then after that, all you need to do is renormalize this in order to have something invariant under the first Kirby rule. So, so you define here the WRT invariant in the SL2 of psi. You take FL of psi, and you divide by, this is F of U plus of psi to the sigma plus, and then FU minus of psi to sigma minus, where sigma plus, sigma minus here is the number of, so plus or minus eigenvalue of the linking matrix of F. Just some normalization to take care of the first Kirby rule. Okay. I mean, this one is invariant under the second Kirby rule. Oh, I have about
5 minutes. Actually, a little more, 7.
Okay, then probably I should. So this is the well. At least I gave you the definition in the
I'm
case
sorry,
of
what is L?
So L here is the link from which you refer. So M here is up to
From which you construct them, okay.
Yeah. Okay, so let me return to the theorem here. Well, in general, it's hard, I mean, from this definition to go to, because in the definition, you see we take the sum from 0 to R, which is the order. And so it's hard to relate to something that is independent of the order here, okay? But as I said, I mean, when you look at the right-hand side there, one way to regularize the sum is to look at root of unity. But there's another way to regularize the sum is just to let Q arbitrary, but then more or less we will go to this type of Habiro ring here. Okay, now let me discuss the some consequence of this theorem here. The first consequence is the integrality. So I already mentioned last time that already from the beginning, Kontsevich at that time told me that all these numbers here, I mean the WRT invariant should be algebraic integer. And then later, Rudolph in some papers explicitly formulated a conjecture. And so a corollary, the first corollary, so there's some consequence. The first one is that if M is an integral homology tree sphere, then the WRT invariant at any root of unity will be in Z of psi, because if you have that function, if you have any root T is in that ring. So in particular, it's an algebraic integer. Or there's a long history about, I mean, the integrality of this, but because I don't have time, so I will skip that. Let me go to the second consequence, which is the relation between the WRT invariant and the NMO invariant or perturbative invariant. So first, the picture is in the not case is the following. So this is a relation to NMO invariant, or this is universal perturbative. Invariant. So the not case is the following. So here you have the set of R naught, and then you have this jk of g v that will map to the set of Laurent polynomial. Okay, so this is the invariant that we talk about. It's just the curvature Jones polynomial. And then you can define, expand this q is equal to t e to the h. You get to formal power series in h. Okay. On the other hand, you can have here the conservation integral. So this is just which takes value in the algebra of chord diagram. Okay, and then to every g and v, you have a so-called the weight system, g, v, that will give us, I mean, from this, an element of chord diagram give us an element in this ring here. Okay. And the statement that this is commutative, so it means that you can actually recover all the quantum invariant coming from Lie algebra from the conservation integral. The proof of the commutativity of this diagram was in the work of Kassan and also independently in the work of Murakami and myself. But actually, this is presumably known to Kontsevich, and the expansion from here to here. I mean, when you will get the coefficient of the perturbative invariants are first studied by Berman, Lim, and Barnata. Okay, so now we want similar.
Excuse me, can you explain the lower line? Because the weight system takes values in the universal enveloping algebra, and here you have a...
No, but you have the v here. You take the you have this v, so you take the trace there, and then you get things.
Then you have a number,
Yeah.
not a series.
Yeah, we have a number, and the series comes from the gradient of this chord diagram here. The h comes from the gradient of this. But I can tell you
Okay.
more detail later. Okay, so now in 2 minutes, let me explain the similar picture for 3 dimension for integral homology 3 sphere. So we have, it's a bit more complicated. We have here the set of all integral homology 3 sphere. So first we have this unified invariant that we and Habiro defined. So that takes value in the Habiro ring. And then from here, you can use the Taylor expansion at 1 to go to the set of formal power series in Q minus 1. Okay. Now, part of our work is that if you put here Q equal to a root of unity, you recover the WRT invariant. So this is the WRT invariant. So now because we have Q here still a formal variable, we can make the substitution Q equal to e to the h. And you go to, again, formal power series in h. Okay. So now this is the NMO invariant, which takes value in the algebra of dry graph. Is a universal finite type invariant, and then so it doesn't depend on any Lie algebra, but so this is also a G here. So whenever you have a Lie algebra, you again have this map, which maps the trigon graphs to the space of to just formal power series. Okay, and the statement is that this, without this one here, this diagram here is commutative, and here we use the work of Barnatan, Verofalidis, Rozanski, and Tursen on August integral. So in the work, and we show that this is more or less this is just the Habiro, the Otsuki series. But the thing is that this is certainly injective here. So once we have this commutative diagram here, so see, once I have this NO invariant here, it's determined this in here. But because this is injection, this is also injection, so once I know the image here, I know that this this is totally determined by this one here. But if this is determined by the NMO invariant, then the WRT invariant is also determined by the NMO invariant. Okay? So that is the way how we can recover the WRT invariant from the universal finite type invariant, the NMO invariant. However, as I said, it's not quite easy. I don't know any algorithm from the Taylor series to recover this one here. But at least we have the statement that the NMO invariant for integral homologous tree spheres dominate on the WRT invariant in this case. Okay, I ran out of time, so thank you.
If you had another minute, what would you say in it?
Well, probably I would say about the, how I define this unified here, but it's probably
How
more
you
than
define the unified?
yeah, the unified, this invariant here, but this probably takes more than a minute, so I
Okay.
yes.
What about the case of rational homology spheres?
Okay, so this is more complicated. We have only this result here. So this is the in joint group with Bediakova and Bühler. So if M is a rational homology tree sphere, so that H1 and Z is just some finite number, which is equal to D, then there exists a unified invariant, but we can only got the result for HL2, which now belong to an extension of the Habiro ring. So in this Habiro ring here, we have to add inverse of D, where D is the size of the group, of the homology group. And then from the WRT invariant can be recovered from this unified invariant here. Okay. However, this ring here is in general not as nice as the Habiro ring. It's in general, if D is bigger than 1, it's not an integral domain. It's not an integral, and we still don't have this kind of diagram for the case of rational homology tree sphere. So we don't know if the NMO invariant in that case will dominate the WRT invariant.
Let's come again.
So we will meet again at 12:15 to listen to Eric Rowe.